basically working on disc bearings, and they are presently in use in many kind of structures, buildings, bridges, most widely used in bridges, but also used in buildings. They are preferred in many situations due to their simplicity, because of their durability, and because of the there are minimum number of parts. They have low maintenance, so there are many distinct advantages which which find, because of which it finds its application very widely in bridges. In general, I would like to clarify here that the bearings are specified and approved for use for essentially to take three kind of loads and movements. One is the vertical load, second is the lateral load or horizontal loads, then the rotations and the translations. These are the basic loads that a bearing is supposed to take, so that it can effectively transfer the loads from superstructure to foundation, the desirable ones, and basically relieve the substructure and foundation from undesirable forces and rotations. Now, although it is usually possible to design all types of bearings that generally are in use, for example, pot bearing, spherical bearing, elastomeric bearing, or disc bearing, for majority of the kind of loads that I described. But usually, uh, for a given situation, one of these type of bearings will be more suitable, and every type of bearing has its own distinct application. They have their own merits and demerits in their specific area of operation. So it is not that if we are saying that this bearing is has got so many advantages, it does not mean that the other bearings do not have its application. So we have to keep that in mind, always. uh, One issue before I hand over to our moderator, Professor Mahesh Tandon, I just want to specify is that I always found a disconnect between the bearing manufacturer, the bearing industry, and the structural engineers. Generally, I find that we structural engineers do not understand the anatomy of the bearings. It is little different from structural engineering, and I mean their process of manufacture, their behavior needs to be, I think, understood by structural engineers well, so that they can recommend a suitable type of bearings and the suitable arrangement of bearing in a given situation. And vice versa, also, I find that the bearing manufacturers need to have a little bit of understanding about the structural behavior of the structure to which they are giving the bearings, so that they are in a better position to recommend a particular type and arrangement of the bearings. In many situations, I found that the structural failure has occurred, or the structure came into distress because of the wrong placement of bearing, because of the wrong orientations of the bearing. And there, I think a bit of closer interaction between the bearing manufacturer and the structural engineer could have avoided this kind of situations. Another aspect which will be covered by the speaker today is the vibration isolation, which which is something which is currently gaining popularity in India. Use of vibration isolation. There are a number of buildings where vibration isolation has been used in India. Uh, our BIS codes are being developed. IRC is also developing codes on the base isolation for bridges. We have at least one or two bridges where this isolation system is now currently in the process of being executed. So I am looking forward to these interesting presentation. I would not take any more time, and I would like to now hand over this platform to Professor Mahesh Tandon, a stalwart in our industry and a kind of a pillar in Indian Association of Structural Engineers, to moderate this session. We have also two panelists, Mr. Nilanjan Ray, Director Metco, and Dr. Suresh Puri, who is the convener of the B6 committee of IRC, which is a committee on bearings. So thank you very much, Mr. Puri and Mr. Ray, for joining this session as a panelist. And before I hand over to Professor Mahesh Tandon, I have the uh, privilege and honor to introduce Tandon Saab. And although Tandon Saab hardly needs any introduction because he is pretty well known in India, but he is the managing director of Tandon Consultants Private Limited. He has designed many structures in India and overseas, which are elegant, which are standing tall, and he is a very well-known figure. He is a fellow of National Academy of Engineering. He is recipient of several awards. I mean, I do not have his CV in front of me, but I know that he is a father figure, a doyen in our structural engineering. And whenever we always lean on Professor Mahesh Tandon for any advice in Indian Association of Structural Engineers. Over to you, Professor Mahesh Tandon, for moderating this session.
Thank you, Alok. And as he said, good morning, good afternoon, and good evening to wherever you are. Whatever applies. Uh, it's a most interesting webinar that I have been asked to moderate, and there is only a single speaker, Mr. Ronald J. Watson, and he's going to talk about design, manufacture, and testing of disc bearings and seismic isolation devices for bridges, buildings, and other civil engineering structures. Uh, our esteemed panel consists of Dr. S.K. Puri, who was the former DG, Director General, and the Special Secretary in the Ministry of Road Transport and Highways. He is currently the convener of the B6 committee, which deals with all types of bearings. The other panelist is Mr. Nilanjan Ray, who is a director of Metal Engineering and Treatment Company Private Limited. I'd say Metco, but that's the name we have known for the last 50 years. Uh, they were pioneers in India in the manufacture of these type of bearings or any type of bearing, starting from the humble elastomeric to pot bearings to you and you name it. And they have also manufactured disc bearings in the past, because I saw one of the structures in which they were installed, and that we can discuss a little later. But let me first uh, uh, introduce to you the speaker, Mr. Ronald J. Watson, who is the president of R.J. Watson Incorporated in the U.S. Uh, he has a Bachelor of Science degree in Civil Structural Engineering from the State University of New York at Buffalo. He has over 40 years of experience in the design, manufacture, and testing of high load, multi rotational bearings, seismic isolation devices, and bridge deck joint sealing systems. As you can see, that his overall experience is uh, well suited to the subject which he is going to talk about. He is a fellow of the American Concrete Institute and serves as chairman of the International Joints and Bearings Research Council. He also chairs the American Society of Testing and Materials Subcommittee, that is the ASTM, D04.32 on bridges and structures. He is the vice chairman of the National Steel Bridge Alliance Task Group 9 on bearings. He is also the president of uh, R.J. Watson Incorporated, which I introduced you to, introduced him as such. And this company specializes in the design, manufacture, and testing of bridge bearing devices and joint sealing systems. Uh, just, I think that I will introduce our panel after the presentation of Mr. Watson is over. But let me talk about a little bit, continuing from what our president, Mr. Alok Bhaumik, had mentioned about bearings. Uh, Bearings are components that is interspersed between the superstructure and substructure. We don't like them, but it is necessary in many situations. If you can't make the superstructure, substructure monolithic or integral for some reason, there is really no other option. Because, really speaking, apart from having a monolithic structure, which we also call integral, which is the best form. Any kind of jointing is, we know, it weakens the whole system. But then there are situations, and these situations are more and more common when you go for a long span, and there is a problem of temperature variations and so many other things which come into the picture, where bearings are essential. So why don't we like them? Because they are the most fragile component of the entire bridge. They are the weakest link in the chain of durability. Their design life is a mere 1/4 of that of the main bridge. They require too much attention for inspection and maintenance. They are a factory manufactured item and cannot be assembled at the site, which means that you have to order it in advance, you have to give all kinds of specifications before they can be ordered, then you check the designs. So it is that these are the things that why we don't like bearings. What's good about them? They have the capability where you have to provide bearings of ensuring that the load transfer between the superstructure and the substructure takes place exactly where and how you want it. They have the capability of providing rotations and displacements in an orderly fashion. These can be unrestrained or completely restrained or even guided restraint. They can act as energy dissipating devices during an earthquake, both for bridge and building applications. In India, we have uh, like the B6 committee, of which Dr. S.K. Puri is the convener. Uh, they have come out with 5 limit state design codes, and these are comes under the category under the name of IRC 83 code for bearings. So part 0 is general design rules. Part 1 is metallic bearings. Part 2 is elastomeric bearings. Part 3 is pot cum PTFE bearings. And part 4 is cylindrical and spherical bearings. As you can see, we don't yet have specifications or codes which will define the disc bearings. But I'm sure that after Mr. Watson's presentation, this will be taken up by Mr. Puri, and some kind of a code, a separate code, because I think it does not fit into any particular category which I have just defined, can be made. So with these introductory remarks, may I ask Mr. Watson to please start his presentation. Thank you.
Okay, thank you,
Sorry, I am
Professor, for that very nice introduction.
Just
I'm
one
gonna.
thing for the participants, if you have any questions, please put it in the question and answer box, and they will get collected there. And at the end, we will ask Mr. Watson to reply to it. And of course, the panel, the esteemed panel, will also interact. Sorry, Mr. Watson, for the interruption. Please
Oh,
continue.
it's okay. Thank you very much for that nice introduction. So the topic is bearings. I think you covered my background, but one point I wanted to make too is I used to work for a company called Watson Bowman, which is a familiar name to many engineers. That was a company my dad started back in 1970. So I worked for him for many years, but he
Okay.
sold the business in the 80s, and then I continued working for the new ownership. But in the early 90s, they decided to get out of the bearing end of the business to focus more on joint systems. And my training and background was more on the bearing side. So that's when I started RJ Watson back in 1992. And then more recently, we acquired one of our primary fabricators. So we're located actually in Western New York, in the Buffalo area, which is on the Canadian border. So we get a lot of snow in the winter. That's what it looks like in the winter in front of our building there. So it's minus 15 today, so it's quite cold. So our shop is broken into three primary areas. We have a machining area where we have vertical, horizontal mills, lathes. Here you can see a plate being machined flat. We also have a fabrication bay, which is where we do the cutting and bending and welding of steel plates. And then we have an assembly area. So once all the parts and pieces are finally put together, then we have the area where we assemble the bearings together. And then the last and one of the most important parts is the testing area. So we have 3 test frames that we utilize for testing bearings on projects. So talking about bearings, I always like to start, what's a bearing supposed to do? And I think Professor explained it pretty well. They have to take loads, movements, and rotations. The problem with the old steel bearings is they're really one directional. They work in the direction of the girder. So the problem we see with these on some structures is where you have evidence of transverse rotation, these bearings are unable to accommodate that. So that's probably what happened here. You're getting some transverse rotation. You can see the bearing is unable to deal with it, so you get the cracking below. The other problem, of course, with the old steel rocker style bearings is they can accumulate dirt and debris underneath the rocking points. So that's what we call the ratcheting effect. And this has been a problem for many years on the old steel bearing. So that's probably what happened here. You get this rocker bearing not able to function. You can see some of the substructural damage. For skewed or curved girder bridges, again, you're getting those transverse rotational forces, and these rocker style bearings aren't able to deal with that. So then here you can see some example of substructural damage. The other problem you can have is that if the bearing seizes up, like this is probably done here, the forces can go into the superstructure too. So here you see a big crack in the girder, emanating from the top of the bearing due to that inability to move. This is kind of an interesting one I saw where the base plate was walking out. Normally those anchor plates are bolted down, but for some reason this one wasn't, and it's sort of walking out from underneath the bearing. We had a bridge up in Albany, New York, that was sitting on one of those tall steel rocker bearings. And during a temperature extreme, it actually tipped over. So this is supposed to be standing upright. So this is supposed to be up here. And it tipped over during a very warm day. And in the process, it almost shoved the adjoining plate girder off the pier. So that steel plate girder just caught on the edge of that pier and prevented it from dropping down. It would have been like, 15 meters down, it would have been a catastrophic failure. So they're very fortunate that didn't happen. They were able to salvage the bridge. Now, the collapse in Minnesota back in 2007 was largely attributed to a gusset plate detone. I think it was this one right here that actually failed, resulting in the structural collapse. But some of the subsequent reports said the bearings were part of the problem too. The bearings on that structure were the rack and pinion geared roller style bearings, very expensive bearings, as you can see. The problem with a bearing like that is you'd have to have some kind of regular maintenance program to keep those gears lubricated. And sadly, I know especially in the U.S., we don't spend a lot of money maintaining bridges. They're not funded, and it doesn't typically happen. So that's a picture of those bearings post-collapse. You can see there's a lot of rust, and again, probably never really were maintained properly. And that was part of the problem as well, too. So Integral designs can be done. I know Professor said he doesn't like bearings, so this is one way of dealing with it. You can have an integral design. If you have good column ductility and connections, that could be an option for you. In this case, probably not a good idea. You can see there's a vertical crack working its way up the column into the beam above, so probably not a good choice there. As was this structure. This is the monorail structure in Las Vegas, and had a hammerhead pier, and they went integral with the design. But look at the cracking that's going on. It actually goes all the way around that hammerhead to the backside as well. Now, had they chosen to use some type of a bearing, they might have alleviated some of the stresses that you see went into that pier. But the workhorse bearing we see used on most bridges is the rubber bearing or elastomeric bearing, typically neoprene or natural rubber, reinforced with steel plates for shear stiffness. So for most of your short and simple span bridges, these work well. The problem, what we see is a lot of owners like these bearings, and then they try to push the envelope and try to use them maybe in applications where they really shouldn't. So we see a lot of big elastomeric bearings being utilized. And most of the problems I've seen with these have been on the very large ones. So here's a very large plan area bearing. You can see some splitting and cracking. That might suggest, you know, some bonding to the steel plate issues would suggest a crack, splits like that. This is one, again, a big plan area here where instead of the rubber shearing, it was abrading off, as you can see there. So maybe that pad wasn't thick enough. So that would be my guess as what happened there. Oftentimes you'll see bulging up on the edges of the pads too. This is a very large one on a bridge in Mississippi. And so, you know, engineers say, well, what's the problem with that? Well, if you cut it open and look at it, that's when you have bulging, that's what's going on the inside. So that would be a sign of some serious problems with that particular pad. Installation problems, again, things like that you see with all bearings. This is a picture I got from a Colorado bridge engineer, and they used these big pads with sliding on top. And as it was cycling, for some reason, it wasn't recovering. So maybe, you know, maybe that's a design flaw. The plates weren't thick enough or something like that. But again, these are big pads that you don't necessarily want to do. And then lastly, we've had a lot of reports of pads walking out. So as it cycles with movements and rotations, the pad is actually walking out from underneath the girder. So that's a problem too. Now, pot bearings were developed as a way to reduce the plan area of a rubber bearing. So you put much higher pressure on the rubber in a pot bearing. In this case, you're going up much higher. So what happens is the rubber becomes unstable. So you have to have some kind of a sealing ring around the perimeter. Now, there's a lot of different materials that are being utilized for sealing rings. But this is where we've seen a big problem, especially in the USA, is these sealing rings, you know, failing prematurely. And of course, when that occurs, then the rubber kind of squishes out of the cavity. So here you can see this manufacturer used a molded plastic ring. It's like molded into the rubber pad. And you can see where that has popped out, and that's the rubber kind of squishing out of the cavity. Here's another example of, again, the rubber on this pot bearing is oozing out of the pot area. This particular manufacturer used brass sealing rings, which are common. But again, if your tolerances are a little bit off between the pot and the piston, the sealing rings can pop out like you see here, and then the rubber kind of squishes out of the cavity as well too. So big problems here in the USA with pot bearings. So with these problems in mind, the disc bearing was developed. So disc bearings, as stated earlier, were developed in the early 1970s. The key is the use of this polyether urethane load and rotational element. Polyurethanes have tremendous compressive strength, excellent weathering properties, and it also has a very wide operating range. It remains stable and flexible from -70 to +120 C. So for normal atmospheric conditions, it remains stable and flexible. So in its simplest form, as a fixed bearing, it's just two plates sandwiched together. There's a central pin there to transmit the horizontal forces. And the way this works is you're compressing that polyurethane, the material wants to expand, but the friction between the plate and the urethane rubber inhibits the expansion, so you get a bulging effect on the edge of the disc. So the reason for the V-notch in the edge of the disc is to reduce the shape factor and control the amount of deflection that you get under design, load, and rotation. So if I load and rotate that disc, this is what it looks like. So there's the rotated edge, and it just kind of fills in that cavity. Close-up view, you can see what it looks like there. So that's the function behind that V-notch in the edge of the disc. So these are examples of fixed bearings. Again, it's very simple design. If you want to introduce some displacement capability to the bearing, then we add the sliding materials. Now, typically we use PTFE, although there are other materials now being utilized for sliding friction, but PTFE offers the lowest friction of anything. Oftentimes it's lubricated, so you have dimples there, and you put silicone grease in there. Now, we bond it to the upper bearing plate, but we also recess it in there, so it's mechanically locked as well as chemically bonded. Mated up against stainless steel, you get very low friction. Usually, plain PTFE, you get around 2% friction. If you lubricate it, it's even lower than that, even less than 1%. So now you have a bearing that can move in any direction, but also rotate in any direction as well, too. And then the third standard type would be guided or one directional. So now we're putting guide bars on there to control the direction of motion. And we also put the sliding materials on the guide bars as well, too. So there's a guided expansion bearing on a bridge application. So lots of different structures use disc bearings. This is a steel plate girder bridge. This is in Oregon, kind of a nice picture there. You can see a curved girder, disc bearings supporting the steel plate girders. This is one in Pennsylvania, big, tall, deep plate girder. And then you look at the bearing, it looks like it's too small to accommodate that load. But the polyurethane we're using has tremendous compressive strength. We load it to 35 megapascals, which is the allowable, but the ultimate strength is probably 20 times that. So you have a tremendous safety factor in the vertical load carrying capability of the polyurethane. Big project we've been working on for several years now is in New York City. It's LaGuardia Airport. So they're spending $8 billion to redo LaGuardia Airport. So it's crazy. But we've got lots of bearings. So when they redo the terminals, they redo the roadways in front. So there's over 1,000 disc bearings at LaGuardia Airport now. So here's an example. Again, the challenge here is how do you get those girders in? You got a roadway here, parking structure there, not a lot of room. So it's really kind of interesting how they got those girders in there. So here you can see some of the disc bearings supporting those plate girders. This is a big project that we did in Cleveland, south of Cleveland a little bit here, not too far from Buffalo. So these are parallel plate girder span bridges. This is kind of an interesting project. It's the most heavily traveled bridge in Ohio. They're 40 years old, but really it's the issue is traffic. So rush hour morning and afternoon looks like that. So they needed to expand it. So what they're doing is they're going to build a new bridge in the middle. And then once the new bridge is finished, then they'll switch traffic back over to the outer sides. So they have this little erection gantry here that they use to drop the girders in place. Here you can see a picture of that. So that spans the two existing bridges, and they pull the girders up from below, so you can see how that works. But 133 bearings on that. The loads are pretty standardized, not too high. Rotations, not too crazy, but some of the horizontal loads are quite high, 40% in some cases, and the movements are standard except for the hinge bearings, which would be 25 or maybe 600 millimeters of movement. So there's your masonry plates, then you weld the lower bearing plate to that. There's some painting going on as well too. You don't paint the surface that comes in contact with the disc. That's a sandblast surface. You want a roughened surface there. Then they're fully assembled. So there you are. We're doing a field weld. Again, when you're field welding, you want to maintain certain temperature limitations so that you don't overheat the PTFE or the polyurethane, so that care has to be taken for that. There you can see one of the installed bearings. Then we always put like a little information plate on each bearing with the manufacturer, date of manufacture, the bridge, the bearing type, and all the pertinent information is on there. So there you can see that's the new bridge. Now they're going to retrofit the existing lane. So it's kind of a cool project. Here's a neat bridge. This is a Delta frame design. So the bearings are actually down here, below here. This is in West Virginia. And there the bearings are shipped to the job site. And then you set them up on spacers, and then they're grouted into place. And that's the finished bridge. So those bearings actually are quite easy to inspect since they're down so low. Steel boxes use disc bearings. This is in Orlando, Florida. In this case, they have two bearings supporting the steel box. Nice looking detail for a bridge. This is another steel box application. A lot of different designs for interchange exit and on ramps. This is a SPUI, single point urban interchange. So these are ways to deal with traffic getting on and off the bridge. These are steel boxes. So it's interesting here. They have 2 bearings on these boxes and then 1 on the outer boxes. So interesting design detail there. Steel arches. This is the Selwood Bridge in Portland, Oregon. Little shout out to the iron workers who built that bridge. So there's one of the bearings at the abutment. You can see the disc bearing being installed. So there's also bearings on top of the spandrel columns too. And then there's bearings, actually lateral bearings between the shear block and the arch rib. So we do a lot of lateral bearings as well too. So there you can see a disc bearing that's installed like that. Now, the lateral bearings are only maybe activated during wind or seismic loads, but the nice thing about the disc bearing is that it can accommodate rotations at low or even zero load. There's no minimum load required for that bearing to accommodate rotations. So we do quite a few of these lateral bearings on big bridges. This is one in Arkansas. This bridge sits on disc bearings as well, too. Nice looking structure. But they had an interesting application during the erection of the arch ribs here. So they have these temporary struts, as you can see here. But at the base of that strut is a rotational disc bearing. So you can see a close-up shot. They painted it white, so you can't see the red disc. But that's what they used for temporary erection of those struts. Kind of a nice picture there. That's in New Mexico. We did a retrofit of this bridge. We replaced the old rocker bearings with disc bearings several years ago, but I thought that was a nice picture. We also worked on the Hoover Dam Bridge. This is in the Nevada-Arizona border, not too far from Las Vegas. If you're ever in Las Vegas, this is not too far away. But this is a North American record. It's about a 320-meter span for a concrete arch. 24 disc bearings are on the tops of the piers there. The taller piers are actually integral. They don't really need a bearing because there's good ductility there, but the shorter piers have bearings and at the abutments too. That's actually the rendering. The renderings are so good now, you can't tell them from the real bridge. But most of the specifications we deal with have a replaceability detail being required of the bearing should something go wrong, that you can get at it and remove it. So here's a pretty typical detail. You have a cast-in plate, but the upper bearing plate is bolted into that. Similarly, you have the masonry plate grouted in, but the lower bearing plate is bolted into that. So to facilitate removal, you would jack the structure, draw those bolts out, and you can pull the bearing out in one piece. That's about 300 meters up, which is a little higher than I normally like to go when I'm looking at bearings. But these bearings are big, but in some cases slide bearings, so they can move around on you during installation. So oftentimes we'll put external hardware like this on the bearings, which connects the upper and lower plates. It's slotted, so you can adjust it for the temperature setting. And then once the final connections are made, then you take that hardware off. So that's the real bridge. That's the finished shot. So it's a pretty cool bridge to be involved with. Cable stay bridge over the Willamette River in Portland. And interesting, they built this bridge for transit only. So you build a big cable stay bridge over the river and they don't allow cars on it, just metro buses and light rail. So there's one of the bearings on that. This is kind of a good picture because people always say, well, how long do these bearings last? Now, these types of bearings should last the life of the structure. But one of the factors we see that inhibits that is deck drainage. If you have your deck water pouring on the bearings, you might run into problems, down the road with the corrosion of the plates. The polyurethane pad is not going to be affected, but the steel plates can be. Now, the reason this was like that on this bridge, they had not installed the joint yet, so that was temporary. But that's something when you're doing your inspections, you want to monitor that the deck water is not pouring down on the bearings, especially up in our part of the world, where we dump road salts, de-icing salts on the highways. That salt water getting down on the bearing could cause problems. So that's something you need to deal with. Pedestrian bridge, kind of a nice one in Ohio. There you can see one of the disc bearings for that. It's got uplift restraint. I'll talk about that in a minute. Another one in Chicago. So we do a lot of pedestrian bridges as well. There you can see the bearings for that bridge. So this is the new bridge that replaced the one that collapsed in Minneapolis, the I35W Bridge. Now it looks integral there. It doesn't look like there's any bearings, but there's actually a gap right here where the big bearings were located. 54 disc bearings. Now some of the bearings on that were designed for 25,000 kilonewtons. So that's a disc for a 25,000 kilonewton application disc bearing. You can see the size of that. There's the main pier where the big bearings were located. And there you can see some of the bearings installed. There again is that replaceability detail, bolted, accessible connections. I say new bridge, it was actually 13 years ago, so it's not so new anymore. But that bridge, start to finish, 11 months. So if you get everybody on the same page, you can do stuff like that. This was a retrofit we did, I-75 up in Saginaw, Michigan. The original bearings were pot bearings. All of them failed. There was like 130 of them. And they had the sealing ring failures, and they decided to replace them. So we replaced them with some disc bearings. So some of the bearings on this were designed for like 35,000 kilonewtons. So now you're getting even bigger. That's a big bearing. So the yellow things, those are the temporary hold downs. The reason we paint them bright yellow is a reminder to take them off when you're done. I forget which bridge it was, but I went out 2 years later and the temporary hold downs were still on there. So we paint them bright yellow just so people remember to take them off when they're done. But that's a big bearing. Here you can see it being installed on the bridge on the retrofit application. So that was quite a nice project for us. And this is what we call an extra dose bridge. I know there's extra dose bridges in India as well too, but extra dose bridge is a cable supported bridge, but instead of the big tall towers, you have a short squat tower. So this is cost effective in a certain span range, but the main pier here, big heavy concrete bridge, some of the bearings were designed for over 45,000 kilonewtons. So big bearings. So a disc like that is 1.5 meters diameter and maybe 300 millimeters thick, something like that. So big giant disc for that project. So fully assembled, each bearing weighed 21 tons. That's a picture of me laying on top of it so you can see how big it is. So massive bearings on that project. So there's a picture of them doing the installation. They're sitting there as I was watching this, hoping those anchor bolts line up with those holes, but it worked out in that case. So of course they wanted that tested. We didn't have the capability to test a bearing that big at our facility. So we went to the California Caltrans facility at University of California at San Diego. And they have a big test frame. They can go up to like 60,000 kilonewtons vertically. They also have lateral actuators. They can do seismic simulation with this big test frame, but gives you an idea with the people off to the side how big that machine is. So there we are doing the testing on that for that bridge in Connecticut. But we have quite a bit of capability ourselves. We have a test frame that goes up to maybe 40,000 kilonewtons. And there's the vertical actuators, lateral actuators for horizontal or friction testing. There's the big, we have a large displacement actuator. So we can do like plus or minus 650 millimeters, you know, on a test frame. So if you have some large displacement bearings, we have that capability to test it. This is our big displacement test frame. We also test expansion joints with that as well too. So there you can see what that looks like. And then a smaller test frame for smaller bearings. This is used quite a bit as well too. So typical, just to talk a little bit about testing, typical testing, you have to test 2 bearings per lot. Lots are usually limited to 25 or less bearings. They're usually bearings of the same load category and type. So they might be broken into fixed and expansion bearings. And then we usually run vertical load tests, rotation tests, friction, and then horizontal load tests are fairly typical as well too. So here you see a load and rotation test. Normally it's about 150% of the design load, and then you rotate it. And you're looking for, you know, separation, liftoff, and then the load is applied for anywhere from an hour to 12 hours. Every state is different, so it's like 50 different countries here, but keeps us on our toes. And then you inspect it afterwards. This is a friction test. You can see we're pushing on that plate. There's the sliding surface up there. For smaller bearings, you can test 2 at the same time. So you have the slide plates on this connected to this plate, and then you shove it back and forth. You can do 2 bearings at once. And then this is a horizontal load test. We have the external actuator. In this case, we use actuators inside the test frame. So we're pushing on that plate. This is your reaction plate above, and then you're doing horizontal load verification testing. Another test that's popping up in the States is the long-term deterioration testing, cyclic rotation testing. So this is our cyclic rotation test rig. So we're pushing that lever arm up and down, and then that rotates the bearings in the test frame there. So these types of tests take a long time. So normally they're used for vendor qualification, you know, anywhere from 5,000 to 15,000 cycles. So you're talking months of testing, you know. So a lot of the manufacturers are required to do this to get approved for certain states. A little bit about design. I know we could talk all day about design. I just wanted to put a few slides in here. So this is the information that we typically need for designing a disc bearing. We need to know what types you're looking for: expansion, fixed, vertical loads, uplift if applicable. Uplift loads are fairly common now, but you have to decide if you have those. You know, your horizontal, longitudinal, and transverse loads, rotations, movement. Again, where plus or minus, longitudinal, transverse, substructure. Is it steel? Is it superstructure? Is it steel? Is it concrete? Same with the substructure as well too. And then these are some of the design aspects for disc bearing: the polyurethane, compressive stress and strain, the thickness formula, rotation. Those are factors in the design of the disc. The shear resistant mechanism or the central pin, bending and shear stresses. The upper and lower plates, primarily bending you're looking at for the sole and masonry plates. Also for masonry, you have the concrete, allowable concrete stress on the concrete. And then for anchors, you have the shear stress and the clearance checks. And then the last thing would be your sliding materials, you know, top and side, PTFE, average and edge stress, contact and edge stress, guide bars, bending and shear stresses, and then of course your connections, whether it's welded or bolted. So these are all the factors that go into the design of a disc bearing. But if I was saying to our friends there that if you want to actually do a design session, we could orchestrate that as well too, where we actually go through some real designs. Uplift, as I mentioned, is quite common now, especially in seismic zones, because earthquakes just don't go back and forth; they go up and down as well too. So seismic designs have uplift often. Sometimes a curved ramp might have a negative vertical load. But the one we're seeing a lot now is flood-prone regions. And we saw that during Hurricane Katrina, where sections of Interstate 10 floated away. You don't think of bridges being buoyant, but they can be with a storm surge. So that might be another reason to use an uplift bearing. Modified pin design, kind of like a trailer hitch on your automobile. You're connecting the upper and lower bearing plates through that. And then if you want movement, the guide bar would then lip underneath the upper bearing plate. So fully assembled, that bearing can move and rotate and then resist uplift as well. So that's a common design. We do a lot of bridges, but we've actually done some buildings with this too. This is the arena up in Calgary, Canada. It's a hyperbolic paraboloid ring beam, and it's supported by uplift disc bearings. So there you can see a good example of a building application. But lots of bridge applications with uplift. I think I showed you a couple already. This is the Cable Stay Bridge up in Maine, Penobscot Narrows. Kind of a neat bridge. They got an observation deck in the one tower, so you can actually take an elevator up to the top and look out over the countryside. So there's one of the uplift bearings for that. That had large displacement as well too, high uplift capability. This is a project out in West Coast, Seattle area, part of the rapid transit system. You can see a precast segmental design with uplift bearings. In this particular pier, they use these shock transmission units or lockup devices. There's a company actually in Buffalo where we are that makes those, a company called Taylor Devices. So there you can see the dampers and associated with the bearings. This is in New York City, Atlantic Avenue Viaduct. They were replacing these girders on nights and weekends so they could maintain the rush hour trains. But there's a little hinge detail there where the bearing had uplift requirements. So the problem is we didn't have a lot of height to work with, so we had to come up with a modified design. So the actual design, instead of the guide bar lipping underneath the upper bearing plate. We used a wedge plate design like that. So that enabled us to achieve the uplift in a much lower profile. And this is a project also in New York City. It's the Kosciuszko Bridge, and that had uplift bearings. So there you can see the uplift pins there being installed, and that's what it looks like with the guide bars with the lips on it. So it's another uplift application in New York City bridge. Of course, we do a lot of international projects too, and we got involved years ago in the Bandra-Worli Sea Link Bridge in Mumbai. So that bridge sits on disc bearings as well too. So those were manufactured by Metco in their facility in Kolkata. And there you can see some of the bearings with the nice galvanized finish on there. And this is a picture of one supporting the big segment there. So that was an interesting project to be involved with. Beautiful bridge. Another one that has disc bearings is the second Vivekananda Bridge. And that's, again, what we call an extra dose bridge, cable supported, but not big tall towers, short towers like that. So that bridge sits on disc bearings as well too. There's a picture of one of the bearings installed on that. This is the Port Mann Bridge in Vancouver, BC. That sits on disc bearings. There you can see one of the bearings for that. Also lateral bearings. Again, this is between the deck and the tower. We talked about lateral bearings previously, and you can see what that looks like. This is a retrofit. This is the Manhattan Bridge in New York City. It's over 100 years old, and the original bearing design was this rocker nest, like you see. That's what they call those when they put rockers together. But you can see where the bolt had sheared off the last rocker there, so they decided to replace these with up-to-date bearings. So there's the disc bearing design. Kind of an interesting design. It's a common masonry plate for two discs, and that was what we came up with to fill in that gap where the old rocker bearings were. There's another bridge in the New York City area. This is the Gotham Bridge. And there you can see the bearings with the upper beveled plate to accommodate the grade. They're going to be cast into the superstructure. Stainless steel hardware. Again, that's a detail we're starting to see being utilized, because if you want to replace the bearing, the bolts need to be able to come out and the nuts need to be able to come off as well too. So stainless steel is starting to pop up. Outer Banks of North Carolina, segmental bridge design. There you can see one of the disc bearings. There again, your temporary hold downs painted bright yellow as a reminder to take them off when you're done. Picture of the sunrise there over the bay. Another beautiful segmental bridge in Virginia Beach, Lesner Bridge. There you can see the bearings being installed on that as well too. So high rotation is another thing that pops up quite a bit. Typically, the standard disc bearing can get anywhere from 2 to 4% rotation, but we've seen higher rotations in some cases. We had a project in Texas where they wanted 8% rotation. So this is our design. It's kind of a modified disc design. It's like not unlike a pot bearing where you have a cavity where the polyurethane is put in. You don't have to seal it because we're not overstressing it. But we use the outer wall for high rotations or high horizontal forces, and that's a picture of that bridge. Beautiful bridge. That's Calatrava design, famous architect, San Diego Calatrava, on that structure there. There you can see one of the disc bearings with the bevel plate, and they drop this steel beam on top of it there. Close-up shot of that. Just a nice substructure design. I thought this is a bridge in Vermont, segmental design, but they jazzed up the piers with that brick-like work. So it looks like a masonry pier. It's not really a masonry pier, but it looks like it. So thought that was kind of nice looking. There's one of the bearings for that project. We got an order for one bearing once. I'm thinking, well, what is that for? It was actually this tent structure. So halfway up that column, it splays into 3 columns, as you can see there. And so there's actually a disc bearing in the middle there that allows rotation of that structure. So in behind all that emergency lighting is one disc bearing. I thought I'd get a discount as a BMW dealership. I thought I'd get a discount on a new BMW. And he said, no, that doesn't apply. So I still drive a Jeep. So curve girders create problems for engineers in trying to determine the direction of expansion and contraction. And I think if you go by the rule book, you go from your fixed point to your expansion point and you draw a chord. But I mean, who's to say that's the way the bridge is really going to want to move? One of my favorite curve girder bridges is this one in Japan. So imagine trying to predict which direction those bearings are going to move. But what we see is I've seen guide bars misalign. I've seen guide bars shear off. So in this case, looks like it's about to shear off there too. So what you can do where there's uncertainty about the direction of displacement is you can put some of the polyurethane pad on the guide bars. So what that gives you is a little bit of lateral flexibility. It's a tight fit, but it gives you a little bit of lateral play in either direction. So that's what we call flexible guiding. So here you can see the flexible guided bearing on that bridge. This is another one in West Virginia. You can see, again, curved ramp. So they wanted to use flexible guided bearings. In this case, we colored it yellow. It's a little bit softer material than the load element, so we changed the color on it. So a lot of light rail. This is the Washington Metro in DC. The Silver Line, which goes out to Dulles Airport, has over 2,000 disc bearings on it. They'd had problems with rubber bearings and pop bearings, so they decided to use disc bearing on this segment. So precast segmental design, there you can see the disc bearings. So not real big, but there's a lot of them. So that's a good application. We do a lot of light rail work. This is one in San Diego, a steel plate girder bridge sitting on our disc bearing. There's their replaceability detail. They have an extra sole plate, and then the bearing sits in a recess so you can pop it out if need be. Class 1 or the heavy rails. This is a project in North Carolina. You can see disc bearings being used. Now, ARIMA is the guidebook for railroad bridges. AASHTO is what we use for highway bridges. A little bit different spec, but they have a disc bearing requirement and specification in ARIMA. They do not allow pop bearings in railroad bridges in the USA. This is a heavy rail bridge in over the Ohio River. They had the original design on this main span was to be a swing bridge, and actually swung it open once or twice after they built it, but it's over 100 years old now. They hadn't swung it open, so they removed the old wedge plate bearings and installed some new disc bearings in place. So there's a good example of a retrofit on a rail bridge. And then we're building these bearings right now. This is a rendering of the new Merchants Bridge in St. Louis over the Mississippi River. And big bearings on that one. So you can see some of the discs are quite large on that. And that's the slide plate. And you get an idea how big that bearing is. So big, massive bearings we're building that. A couple of ongoing projects we got going right now. This is the LAX people mover at Los Angeles Airport. That's that famous tower there at LAX. So they're building the new people mover. So they actually got not a lot of bearings, but they're big. They're in California, so big seismic design. So here you can see some horizontal load testing that we were doing for that. They actually sent 8 engineers out to witness this. This was just before COVID hit last year. So they had 8 people come out to witness the testing. There you can see one of the bearings being installed on that project at LAX. We're also working on the high-speed rail in California. They're building it. The goal is to go San Francisco to LA. Right now they're working on the section from Bakersfield to Fresno. So it's this section right in here. So there you can see some of the construction of the high-speed rail in California. Lots of bearings. So we got 400 or so disc bearings going in on that section. So nice thing about that job is there are a lot of the same, so we get to make a whole bunch of the same type of bearing. This is one in DC, rendering of the Frederick Douglass Bridge. Big slide plates on those bearings, as you can see there. There's some construction shots from the summer. And then this is the new rendering of the new Ganga River Bridge near Sultanganj. But that's a project that Metco's working on right now. They've actually fabricated some of the uplift bearings, and there's a picture of one of them. So this bridge has service uplift. So for service uplift, what we do is we have a dual disc design. So there's your vertical load disc, and then you can't see it, but underneath there's an uplift load disc. So when this goes into uplift, it pulls on and loads the disc below. So it's a dual acting uplift type bearing. So beautiful looking bearing in Metco's facility there. So we had a project in Texas, Fort Worth, and they were dropping these arch ribs down on top of the bearings. They had some kind of an accident, crane tipped over or something. So what ended up happening is all the load ended up on one edge of the disc. So there you can see a picture of it. Actually, the entire weight of the structure was pinching the one edge of the disc. So the contractor called me up and said, hey, I think we're going to have to replace some of these discs because we had this construction accident. So I said, well, jack it back, and see what it looks like. So they jacked it back, no damage at all. So that kind of gives you an idea of the durability of these polyurethane pads. Another good example of durability was this bridge. This is a bridge we installed some disc bearings on in Canada back in the 80s. Then several years later, they changed their seismic criteria. So all of a sudden, they had bearings that didn't meet the new spec. There was nothing wrong with them. They just weren't designed for the loads. So since it was a lifeline structure, they decided to replace the old bearings with our new isolation bearings. But I got the contractor to get me some of the bearings, and we took a look at the discs. And this disc was in service for 32 years. So really, there wasn't a mark on it. It looked great. It looked like a brand new disc. So what do? We cut up some tensile strips and compression buttons, and then we ran the physical property testing on the 32-year-old material. So on the left is a compilation of tests that we ran on brand new discs, and on the right is a compilation of tests that we ran on the 32-year-old discs. And you can see a little bit of degradation in tensile strength, compression set a little higher, but this still meets the spec. So I could take those 32-year-old discs and supply them for a new project, and the owner wouldn't be able to say no because it meets the spec. Not that we would do that, but it kind of gives you an idea on how durable these materials are. Probably the best example, though, is older installations. So this is a project we did in Hawaii back 30 years ago, the Windward Viaduct, kind of a nice-looking bridge. So these are 30 years old, a little bit of rusting going on, obviously. So our recommendation was to do some remedial painting, but pretty good condition after 30 years. This is a project up in Denver, I-25, I-70 interchange. These bearings were installed in the mid-'80s. So these are 35 years old now. Excellent condition. Again, keep the deck drainage off of them. They'll last the life of the structure. And then this is the Pasco-Kennewick Bridge in the state of Washington. This was actually the first cable stay bridge built in the lower 48 states. So this is a big cable stay span. The bearings were designed for about 650 millimeters of movement at the expansion joint. So there you can see big, long slide plate there. But that's a picture taken of that bearing probably around the time of installation, which was 1976. And I was out there a few years ago and took this picture there. So that's 40 years later. So 40 years old, excellent condition. So good testimonial. The other thing I wanted to talk a little bit about was isolation. So for earthquake design, one of the tools engineers have is to isolate the structure. Basically, you're creating some flexibility between the substructure and superstructure. So the goal is to lengthen the period of vibration of the structure. Now, one of the popular isolation bearings in the U.S. is the lead rubber bearings. You have a rubber bearing with a lead core. So shearing of that lead is what gives you your energy dissipation. There's been some concern about these, so what happens after an earthquake. So they did some testing at the Earthquake Center at University of Buffalo. They did some routine shake table testing on lead rubber bearings, and then they cut them open afterwards. So that's what it looked like inside after the testing. So is this still functional? Well, maybe, but internally you can see there's quite a bit of damage. So that's been a big concern. So with this problem in mind, the disc bearing can be modified for isolation applications as well too. So what we do is we thicken up the upper bearing plate, outfit the perimeter with springs, and the springs act as a restoring force to bring the structure back to where it started. And the damping comes from the sliding friction. So we use this housing to connect the springs to the upper bearing plates. A polyurethane material, a little bit softer than the load element. So this is a test that we ran on 2 springs separated by a plate, and then there's a rod running down the middle so you can get an idea of how flexible they are. So you can do this all day long as you stay in the elastic range of the material. So again, this is kind of like a rubber band. You can just keep compressing it, and it'll continue to exert a restoring force. So not only would it have to compress, but it would have to slide at the same time. So this is representative of what it might see during a seismic event. So we're fortunate, actually located right where we are near the Earthquake Center at University of Buffalo. And they have seismic simulators and shake tables and all sorts of fun testing equipment there. But we did testing on this concept many years ago. So there's the bearings at the corners, and then you have plate girders and lead bricks on top. So we cycled the bearings through like 50 different earthquakes. We got good force reductions, manageable displacements. And then after the earthquake, we just kind of flipped the machine. Now that picture's a little grainy. That was probably a 8mm camera back in the day, but that's more like a durability test. So you can see the shake table shaking away, and those are the yellow springs that are shoving that back and forth. So after the 50 earthquakes and then the durability tests that we ran, that's what the bearings look like. Still functional. So they still work after 50 earthquakes. And that's important because earthquakes don't come as one event. There's precursors and there's aftershocks as well too. So there's our seismic high-speed test frame. We actually built this frame and donated it to the university. So all the high-speed testing that we do it at the earthquake center there. So lots of projects. You know, you always think of California when you think of earthquakes, but I think it's like 39 out of 50 states have seismic issues, and New York has seismic issues as well too. I think the big difference is frequency. They have, you know, much more frequent earthquakes out west, but the potential back east is just as good. So here you can see the ramps in and out of Terminal 4. So if you fly into JFK and then leave, you'll be going on these ramps. There's the isolation design, spring design, that fits over top of that. So fully assembled, that's what they look like. And there's a gap there. You can see the springs and the disc. So you can see how that works. This is our airport in Buffalo. We have seismic issues there too. The engineer didn't want square bearings. He wanted round bearings. So we have an octagonal upper bearing plate with springs around the perimeter. So if you look on top of the column there, that's one of our seismic isolators. This is a project in Arizona. Not a fancy bridge, but that's a lifeline structure. So that needs to be functional after the earthquake to carry emergency vehicles over the tracks. So that's the existing bearing. You don't have to be a seismic expert. Look at that. Picture some ground motion. You can see where that could be a problem. So we drilled new anchor bolt holes outside the existing masonry plate, jacked the structure in, and shoved the new isolators in place. So that project, they weren't real big bearings, but there were 16 of them, 16 isolators. And the whole project was just replacing the bearings. So the total cost was $70,000. That's including jacking, removal, and replacement. So not crazy money to seismically upgrade a lifeline structure. This is one we did in southern Illinois, replacing the old rocket. There was 481 of those that we replaced. So there's the new isolator that we supplied for that. Retrofit of an old historic truss. Again, the other thing you can do is you can change the stiffness in different directions. Usually laterally, the springs are a little stiffer than the longitudinal springs, but that can be done with this type of bearing. The bearing, people often ask, are those springs loose or are they press fit in there? And the answer is they're press fit in there. So this is our 40-ton jack to compress the springs. These are set screws that hold them in place. Then once the springs are pre-compressed, then they're put inside the box. And then we release the pressure once they're in there. So that's how we make them. Nice looking bridge up in Canada, sitting on our isolation bearings. Also have uplift restraint as well as isolation. So those two features combined. And one of my favorite projects, this is the Atmosphere condo in Kolkata. It's got a sky bridge. Sky bridge is huge. There's like a health club, nightclub, pool, trees all on the sky bridge. So there's 4 isolators, 2 at each side, but they're massive. They're really big bearings. And we actually made those here in Buffalo and shipped them out to the site. So there's the workers. I thought that was kind of cool. They were putting like religious artifacts on the bearings to bless them, and then they were lifting them into place. And there's the installation. So that was an interesting project, supplying big isolators like that. That's I think that was a recent picture. Somebody sent me that. So they got the trees on there. This is another interesting building project. This is the Unisur building in Ecuador. And he's got these cantilevered sections of the building. This building's right on the equator. So half the building is in the northern hemisphere and the other half is in the southern hemisphere. But these cantilevered sections were what concerned engineers. They wanted to keep those things from bouncing around too much. So the design of the bearing, so there you can see the disc, but there's vertical springs. So they're concerned with vertical acceleration there. And then these are dampers. So as it cycles up and down, it also dampens the energy out. So the bearings are located here supporting that cantilevered section of the floor. So, and that's actually been through an earthquake. So that's, we know it works well. And then lastly, we did this project in Mexico. I think it was on 2002. And then I think it was 6 months later, they had a big earthquake. So I called the engineer. I said, everything okay? He goes, oh yeah, it worked great. You know, so that's not after the earthquake, that's during construction. But they barged these trusses into place and then lifted them using the pier to lift them. And then they put these corbels underneath there to support the truss. So that went through a pretty good seismic event and performed well. I think in reality, what we do to these things in the lab probably far exceeds what it'll actually see during a seismic event. But nice to know that they work. So quick conclusions, DISTA bearings are cost effective. The field inspections show that they provide long-term maintenance-free performance. They should last the life of your structure. Again, that my cautionary note is deck drainage. You know, keep the deck water off the plates, and they'll last a long time. And then you can easily modify it for uplift, high horizontal force, isolation, or whatever you're trying to do. We can modify these to that. We do a lot of proposal work. So if you had a project in mind, if you can give us, you know, the critical information, we'd be glad to work with you on that. A couple of final points. We've heard other bearing manufacturers express concern over the central pin. You can't inspect it. The pin transmits the horizontal forces. It's hermetically sealed in there. You've got a 35 MPa pressure on the polyurethane pad, keeping, you know, contaminants out from that. So it's not going to corrode. In my over 40 years of experience, I've never heard of any one of these failing, these pins. So it's protected in there very well. The other concern is the rotational resistance of a disc bearing. It might be a little bit more than a spherical bearing, but it's still quite low. So we haven't had any edge pressure failures of PTFE or anything like that as well too. So these are a couple things that I've heard other people say about disc bearings, but really it's the bearing of choice in the USA now. I mean, that's what most engineers are specifying. We also have a marketing alliance with a company called BDI for monitoring. Sometimes engineers want to monitor what's going on, what's the real load, what's the real rotation and movement. That can be done. We work with this company for monitoring. And we also offer joint seals as well too. So that concludes my presentation. Thank you very much.
Thank you. Thank you, Mr. Watson, for a wonderful presentation, and also for showing us slides of so many beautiful bridges, and of course how the bearing functions. I think it was made quite clear. I think it is now time that I introduce a little more about our panelists. First, Dr. S.K. Puri. He took his bachelor's and master's degree in structural engineering from IIT Delhi, and he has some 48 years of experience. He has worked in the National Highways Authority of India, and then he has worked in a number of countries like Nigeria, Saudi Arabia, Nepal, and his present uh, employment is with ICT, as we call it, but uh, it's stands for Intercontinental Consultants and Technocrats Private Limited, New Delhi. I mean, this is one of the most well-known consulting engineering companies in the country, and he's the president of ICT. He has also worked in IRC um, before he became the director general. Before he also spent some time in the IRC and YAPSE. So it's a very good all-round experience, and I'm glad that Dr. S.K. Puri has agreed to join this panel and share his experiences and many questions that he may have. He can have this exchange. This will be the right time. The second panelist is Mr. Nilanjan Ray, who's a director in Metco, and he obtained his BE in civil engineering from the what was earlier known as the Bengal Engineering College. We also know it as Shibpur these days. And he has done some special management programs from Indian Institute of Management, Calcutta. He is involved in multidisciplinary activities of different engineering and infrastructure projects for the last 2 decades. And of course, he has authored some papers in international fora on bearings, expansion joints, and isolators, all different things he has done. And of course, he is an active member of the Joints, Bearings and Appurtenances Committee of IRC. So with this introduction, may I now request the panelists, if they want to pose any questions to Mr. Watson. And Mr. Watson, sorry, I saw only a little later your friend, Mr. Achyut Ghosh,
Oh,
who's in Calcutta, and he was
yeah.
previously in Metco. He wishes you a good morning, and what he
Great. Yeah.
mentioned was that you could, the lighting that you are using
Yeah.
is not very good because we can see your wonderful hair and the background is lighted, but
Yeah.
we would like to also see your face. So he
Yeah.
had suggested, I saw it a little late. Otherwise, I would, yes.
Yeah.
I hope that Mr. Achyut Ghosh is happy with that.
Yeah, I got some backlight here. It's creating a bad look there. So, but
Okay, so Mr. Puri, any interaction with our speaker?
Uh, Thank you, Professor Tandon, and good morning to you, Ms. Watson. It had been a pleasure for me this is the second time I have been attending this webinar. It was really an excellent presentation, and I would admit that in the first presentation, you miss some of the finer points. And when you are attending a repetition, you catch those finer points also of your presentation. So really is an excellent. In the capacity of convener of our B6 committee, this is for bearings, let me admit that as already informed to you by Professor Tandon, that we do not have a code on disc bearings in IRC. Although we really would love to have it. And I think earlier, whenever some discussions had taken place, there were, some kind of reservations. In fact, you yourself have mentioned that there is some myth about this disc bearing in some quarters or some sectors, particularly, I would say, the European. So now
sure. Yeah.
It is obvious that we, like I told her earlier also last time, we had a discussion on this about 2 months back when we had our meeting. And we are interested to take up this issue and have a code for this on disc bearing. In that, we would really need your help in this matter. One is this material. Now instead of PTFE, another material is being used by you, which has those qualities. Now the questions will be, and we would like to know, one, technical, specifications of those materials. Is this material as it is available anywhere in the market? if any manufacturer wants to go in for manufacture of disc bearings, can he get this material? And, there will be so many related questions where we would have to go into the technical parameters of these materials, testing of these finished goods. So it will be my request to, in fact, Mr. Ray, who is in coordination with you, and he is also our one of the very important members of the committee, to help us with some kind of a, documentation, some kind of a paperwork, wherein you can give us some assistance to start to start off with this thing. And then obviously we will have our own discussions, our own experiences. We may again come back to you for further clarifications.
Right.
So that is what I can only say, that takeaway, as far as I am concerned, from your presentation is that it looks to be an excellent, uh, type of bearing, which has all kind of, whether it is the vertical forces, transitions, rotations, is able to capture everything. Uh, like Professor Tandon has said, that normally a bearing life, we consider, let's say 20, 25 years, which is only 1/4 of the uh, life of the structure, which normally we are designing now for 100 years. But you said that this bearing will have the life of the structure, which is a big thing. And considering the cost of the, if initial cost of the bearing, even if it is slightly more, it is worth it, because lifetime costing of a bearing, if I have to change it 4 times during the lifetime of a structure, it is going to be it's going to cost much more. So lifetime costing of the bearing, then it will be cheaper, even bearing, disc bearing, what you are saying with this material. So I would conclude this query, and whatever you have to say, that we would need your assistance to promote and to make some kind of specifications for the disc bearings to be used in India. Thank you.
Okay, thank you. Yeah.
Okay.
I think just a quick reply on that was, the key difference, of course, is the polyurethane, because you have specs now for spherical bearings and pop bearings. Most of the components are similar, like the sliding materials and the plates and things like that. The key component would be the polyurethane, and you'd have to come up with a specification for that, and then the testing of that as well too. But there's certainly lots of codes. There's the AASHTO code in the USA that could be a basis for your use. There's many states have their own codes. As I said, in the USA, we have 50 states. It's like 50 different countries. They're all different, so there's lots of different codes to look at. But that's really the key, is the polyurethane, and coming up with a proper specification for that.
Now, you see, like you are saying, there are different type of codes and different specifications. Now, we would like to know from your experience, which is the
Right.
best.
Right. Yeah. Well, again, I think AASHTO would be a good place to start. The AASHTO code, and they're actually reworking that right now too. We're involved with that, and they're updating it, trying to bring it up, up to, because the code is probably written 20 years ago, so it's time for that to be dusted off and brought up there. So I would suggest starting there, in the first place.
Okay, thank you.
I think perhaps Mr. Nilanjan Ray, who's the member of the B6 committee, he should be the central point in which all this information can be given. And I can just put it in simple language what Mr. Puri perhaps is hesitant to say. Whatever specifications come in the code, they have to be generic in nature. they cannot be made for a specific product or a specific manufacturer. So this is the problem. And if you can get over this, I'm sure that the disc bearing code at least will come in India and it will have a lot of applications. But this is really up to you. I am not very sure.
Yeah, I agree with you both, Professor Tandon and Dr. Puri. The main beauty of the disc bearing code, as you said, the specification of the polyether element is generic in nature, and the major properties, the material properties like strength, tensile strength, elongation, hardness, is all specified in the code. So it will be a generic code, and anybody and everybody who is want to purchase it as, and those who can test it as per the specification, they can do it his liberty. There is no absolute no embargo or patent, nothing is there. So it can be easily brought in the code. And as Mr. Ron Watson said, it is to start with, ASTRO will be the best guideline. And of course, we as a Metco has worked with him for the last 20 years. We can be use our experience and his vast experience and be instrumental to have the code as soon as the situation permits. We drafting the code with all the generic specification and other things.
Yes, I think that once that can be done, we'll I'm sure see a lot of usage of disc
Yeah.
bearings. Um, the one of the questions which is asked is by Mr. Gaurav Nada is about the cost. How does it compare with a pot PTFE bearing?
Yeah, I could address that question because we compete with pot bearings in many cases, in some cases, and the cost is very similar. I mean, the components like the plates and the sliding materials are all the same. The difference is the rubber. So polyurethane is more expensive than traditional neoprene or natural rubber. That being said, though, there's less machining with the disc bearing because you don't have to machine the cavity out for the pot. So what you're spending on the rubber material, you're saving in the machining aspect. So the costs between the two are very close.
Okay. Another question is the life of the bearing is similar to the life of the bridge. What numerical figure did you have in mind?
Well, I
Mr.
think
Rakesh Kumar Shukla.
typically when in the US we're looking at 75 or 100-year lifespan, so, and there's certainly no reason why it can't last that long. That we have, long-term weathering tests that we've run on the polyurethane which demonstrate good performance. As I showed you, we pulled out a bearing that was in service for 32 years. It looked brand new. There was really no major degradation in material properties. So I have no reason to think that wouldn't last, many, many years longer than that. So we have a good confidence level. But as I said, the key is keeping the deck drainage off the bearings. If you got deck water pouring down on your bearings, I don't care what kind of bearing it is, it's not going to last for the life of the structure. So.
Mr. Watson, let me ask you another question, a related question. In the US, when you supply a manufactured item like the bearings, do you have to give a warranty for a certain number of years?
Yeah, that's a good question. Most of the states we work in don't require a warranty, but we have seen that start to pop up now. So we've seen projects where they're requesting 5-10 year or sometimes more. But again, it's different in every state. So normally no, but we're certainly not opposed to that.
So in the specifications, that would be another thing that will come up is about the warranty as to how many years we should make it.
Right.
Of course, with the proviso that you use it correctly and you install it correctly, where I
Right.
think your representatives should be there at the site to ensure
Yep.
that it is being installed properly. And then,
Right.
like you mentioned about deck drainage and so on and so forth, those things taken care of, what would be the number you suggest? I think that's another question which is going to come up.
That's a that's a good question. I mean, I've seen, in some cases 10 years, you could go longer, 25. I wouldn't feel uncomfortable saying 25 years as long as you take care of those details you mentioned, so
Sure.
certainly that's something that I think we could live to. But I think,
Uh, Chandan Saab, may I ask a question?
Yes,
Yep.
yes, Mr. Bhaumik, please.
Yeah, so it was a fascinating presentation, Mr. Watson. I just have a simple question. Why is it that the Eurocode do not cover disc bearing? Uh, I mean, is there any specific reason why this disc bearing is not popular in Europe?
well, I think it's a very simple answer to that because no disc bearing manufacturers, are offering it, so disc bearings are they were developed actually in Canada many years ago, and then I was involved with the company that developed it, and we manufactured here. We don't market or sell bearings in Europe, so with nobody marketing or promoting the product, the Eurocode has no reason to adopt it, so if that were to change, like if I said, well, I think I want to start working in Europe, we would have to work with the code and do it. So I've heard people say they're banned in Europe. Well, that's not the case. They're simply not covered,
Yeah, thank you.
Okay, so Mr. Sushil Dhawan, he's uh, or Dr. Sushil Dhawan, I should call him. He's the youngest PhD from IIT Delhi and also a member of our association. Um, he asks the maximum number of questions. So I will filter them out for you so that you, it's easy for you to reply. One is the how do you do the monitoring of these bearings?
That's a good question. I'm not a specialist in monitoring. That's why we've opted to work with a separate company. I know some of the bearing manufacturers do monitoring themselves, but we work closely with they have load cells that they can use to monitor actual loads. Movement monitoring is pretty simple. You can use some fairly basic stuff to do that. And then there's, strain gauges for rotation, things like that too. But if there's any real serious interest in monitoring, I often, refer to our company BDI that we work with.
Okay. So, of course, then there's Mr. Narsimha Chari, who asked what will be the allowable rotation values, like 650 millimeter displacement. I think he's asking for the rotational values. What kind of values do you normally have in your bearings? What can they take? You mentioned
Yeah.
about some percentages. Yeah.
Standard is usually around 2%, but we can play around with the shape factor of the polyurethane to get upwards of 4% rotation. That'll cover 99% of your bridges. But I showed you that one picture of the bridge in Texas where they had 8% rotation due to the way that bridge was designed. So we actually modified the design a little bit. It almost looks kind of like a pot bearing where we drop the disc in a cavity. So that's a specialty design that we came up with for 8% rotation. I haven't seen anything beyond that yet, as far as rotations goes, but I think that should cover most things.
Yes, I think it should. Mr. Achyut Ghosh has asked if the life of the disc bearing is much longer compared to other types of bearings. I personally will advise making the bearing from all stainless steel. The cost is meaningless considering the lifetime cost.
Yeah, that's a good question because you have environments, like we've done some projects in salt, where the bridge is over salt water, and obviously the salt water, that environment, and then there's salt in the air. So we actually did a project in Florida. It was a bridge over some salt water where we did make the whole bearing out of stainless. It's expensive, but that's certainly one of the ways of dealing with that environment where you're going to be in salt air and 100% of the time.
Okay, Mr. BSC Rao asks a question. He would love to have a presentation specifically on design procedures and how they are actually manufactured. I mean, not the procedure is manufactured, but he wants to
Yeah.
see the bearing being manufactured and also the design procedures. Because in any case, if you have a code on the subject, you will have to give the design procedures also.
Yeah. I mean, that's a different presentation if you wanted to see that. And we would be glad to do that. If the Institute is interested, we could do a design, presentation where we talk, break it down. And then also we could show more details on manufacturing too. What I would like to invite is all of you, invite you to come visit our facility here in Western New York. Maybe wait till summer though. It's a little cold right now, but you're all invited anytime you get into, and then certainly if you come to Buffalo, we have the earthquake laboratory at University of Buffalo, which is very interesting too. We could organize a tour of that as well too. So open invitation.
I think some of the design procedures, some of the design procedures are given in this presentation. There are 2-3 slides. And also he showed some of the manufacturing process at the very beginning. Yeah. In the slides, he has shown some of the steps of the design.
I think Mr. Achyut Ghosh. I think Mr. Achyut Ghosh is in the panel now. Achyuta, you can, just click on your video so that we can see you and you can share your thoughts. Yeah.
Yes.
Thank you. Thank you, all of. Thank you, Ronald.
Oh, good to see you.
Yeah, I met you in Buffalo.
Oh, okay, great. Yeah.
Long time back. Okay. Now, regarding the cost, one point is coming up regarding the cost. I am 80 plus, so you have to permit that clothing. So, the cost is really, it's a meaningless concept. 1%, 0.5% of the cost of the bridge, but then replacing a bearing and changing it in midstream is a terrible job. And when, as Ronald had shown one particular bridge, which is transferring almost 250,000 of 1/10 million of transports per day, then in that kind of bridge, the replacement is almost extremely difficult. So you have to make a new bridge. Now, if the cost of a new bridge comes into the factor, then the lifetime cost of the bridge bearing is a meaningless concept. Kindly bear with me in that. So I will say, when we are making our specification, we make all the parts of the bearing, irrespective whether it is in Bombay Sea or in Bay of Bengal or somewhere else or in the middle of my country. Make it from stainless steel. Make this specification. Why bother? What is the cost? What is the cost?
Right.
That's it. I have made my submission. Thank you, Olaf, for kindly putting me in the view. Thank you.
No, that's a great point, because you're right. The cost of a bearing compared to the cost of the bridge is maybe 1 or 2%, very small. So if you're increasing that a little bit, it's still not going to affect the overall cost of the bridge that much. But we have seen it. We have seen people specify stainless steel plates. So it's an interesting idea. It's always difficult for people to pay more than they have to pay, but there's also some very good protective coating systems too. I think one of the more popular ones now is metallizing spray zinc, so you can spray it on, and that tends to perform a little bit better than painting, and things like that. But you raise an excellent point. I'd be on board if we all went to stainless steel.
Well, Ronald, I may just answer 1 or 2 lines. That is, all the time in your lecture, you were suggesting that it is the idea of the owner to see that the water does not fall on the bearing. But why
Right.
fall? Water will fall. Water has a tendency to go down where gravity is pulling it. And do you think our expansion joints and everything that will be permanently, life of the expansion joint is much less compared to that of a bearing. Now the expansion joint as a leak proof thing, or even water, permitting water not to go down to the bearing is a much more difficult task.
Right.
So giving any form of coating like zinc spray, aluminum spray, and all that, you accept. That is okay. But I think, you make the level playing field. Everybody has to give it in stainless steel. So the field of making is level
Right.
playing field for the contractor. That's my humble suggestion. Thank you.
Yeah. Another point on the deck drainage too, what I've seen happen with some bearing details now is they offset the bearing away from the joint area a little bit. So there's a gap, and so even if it were to leak, it wouldn't pour down on the bearings. So that's another detail we've seen implemented on bridges.
Yes, that's difficult to do all the time. You are shifting the center of holding that, and then a little bit of cantilever will be there beyond the bearing.
Right.
It will complicate the system design.
Right. Yeah.
Okay, thank you, Mr. Ghosh. I think we are fast running out of time. There are a lot of questions, and I think we will send them over to Mr. Watson, and then he can reply to them. Uh,
I'll
I would
just
just
take
like.
1 minute. I'll just take one
Yes,
minute.
yes, Mr.
1
Puri,
minute.
please.
Mr. Watson, what I propose is that we'll make a small subgroup within our committee under the convenership of Mr. Ray. And when we prepare a draft, I'm sure we'll be having a lot of questions in that. At that stage, we'll invite you for this presentation, online presentation to the committee, wherein we can ask. So I think I need your nod for that, that yes, you would oblige us for that.
Excellent.
Yeah, absolutely.
Yeah, this is an excellent suggestion, and thank you, Dr. Puri, for saying this. And I'm sure Ron will be very happy to help us with online
Yeah.
sessions as many times as necessary.
Sure. Yeah.
Let me correct it wrongly. I have been addressed as doctor. I'm not doctor. I did only my master's. I did not do my PhD. So just for correction, thank you.
Sir, your work experience is nothing less than PhD.
Yes, I think they were so impressed reading your CV, they decided to put the doctor before that.
Okay.
So
Okay.
I think that before we close, I just want to say a couple of things. One is, that you showed extra dose bridges. You also showed one in Calcutta, uh, where you have a joint, expansion joint at mid-span. And this requires, if you put a joint in the mid-span of an extra dose bridge, it requires 16 bearings put together to be able to transfer the forces across it. Because many of these extra dose bridges, which we are making now in India, are very long and they require expansion joints. One place where you can put the expansion joint is at mid-span. But at every place you put an expansion joint in mid-span, you require 16 bearings. So we are looking for some kind of bearings which you don't have to change so often, because 16 is not simple. Even to
Yeah.
monitor or to inspect, etc., is difficult. That is one issue which you can keep in mind.
Yeah.
The second thing is that when you have a cable stayed bridge, and let us say the end span, when you look at it, it's always less than uh, or equal to half the main span, which means that even for the permanent loads, you may get an uplift forget about the live load. Of course, you will get additional uplift due to live load. What are your views on the subject of permanent load also giving you an uplift? And can you use disc bearings in these type of situations?
Yeah, certainly I think uplift is an interesting thing. You know, initially when we were supplying bearings, it was like extreme event uplift type things, which we can design for. But I think if you look at what Metco has built for the Ganga River Bridge, it's a dual acting disc bearing. So it's a different animal altogether. So for service uplift, like you're describing, that's what we would recommend. So that bearing has the ability to rotate while in uplift. So that's one of the key things for that. But yeah, I think uplift, if you can get away from it, is probably a good idea. But in some cases you can't, you know, so we have bearing details that can address that.
So you,
may I add a point? Professor Tandon, may I add a point here?
Yeah, please.
Yeah, that's it. For Ronald also. You see, in a cable stayed bridge, you have to make the inner span more weight compared to the outer span, to the short span. So even with full load, that has to be done to keep the bridge operating. Otherwise, there will be no transfer of car from the shore to the bridge. So I think instead of increasing the cost of the bridge, of the bearing, you use external means to hold it down by cables. And that will solve the problem at a cheaper price, cheaper than designing a bearing with 10 times of thrust compared to the downward forces. Thank you.
Yeah, that's a good point too, because you don't always want to do everything at the bearing. You can, but I mean, it gets expensive. So there are probably less expensive ways of dealing with that.
Yeah. Okay. So I think that we are way beyond our closing time. So may I ask Mr. Alok Bhaumik to make his final comments, and then we can close this session.
Thank you, Professor Tandon, for moderating this fascinating webinar in an excellent way. And I thank the speaker, Ron, profusely. I thank him for agreeing to make this presentation and also covering, though very briefly, the design aspects of the bearings. And as he suggested, I would wish that if we can have one more webinar where we only focus on the design and fabrication, maybe a kind of a workshop at a time and convenient to you, maybe after a month or 2 months, I don't mind. But if we can have such another webinar, it would be excellent, particularly for the committee where we are now thinking of drafting a code for disc bearing. So I would look forward to such presentation. I'm sorry, I'm very demanding, and I'm probably asking for too much, but I that's a request from my side. And I profusely thank all the panelists. Mr. Ray, I thank you very much for initiating and organizing this webinar. Mr. Atish Mitra, Mr. Puri, and also not to leave out Professor Achyut Ghosh. Dada, he is a stalwart. Let me tell you, Ron, you may be knowing him, but I know him since I think last 4 decades. In fact, I was in my infancy in profession when I know Professor Achyut Ghosh. At that time, he was with Metco, and he is a stalwart as far as the bearings is concerned in India. So with that, I close this session. Thank you very much.
Thank you.
Thank you.
Okay, thank you.
Thank you.
Thank you, everybody.
Thank you.